Every mineral you see, from diamond to salt, has a story that began billions of years ago in the heart of a star. Yes, the earth beneath your feet is made of stellar material. Welcome to Geology Wonders, your gateway to understanding the science of our planet. In this video, we will explore the origin of minerals, how they form, and the conditions that create them. Section 1. Origin of minerals. All the elements currently found on the Earth originally came from the primordial matter that gave rise to the planet itself. Minerals present in the Earth today are formed and concentrated from these elements, particularly during the cooling of magma. Magma is molten rock rich in elements such as oxygen and silicon. In summary, minerals originate from elements that themselves originated from original stellar matter. Minerals found in the Earth's crust are broadly classified into primary and secondary minerals based on their origin. Primary minerals. Primary minerals are formed directly through the consolidation of magma under suitable conditions. Therefore, minerals that constitute igneous rocks are of primary origin. In some cases, primary minerals may also form directly from the vapor state, particularly in regions near active volcanoes. Examples include sulfur and certain sulfides of arsenic. Secondary minerals. Secondary minerals are formed through the crystallization of solutions containing relevant ions. Minerals such as halite and borax typically originate from aqueous solutions. Additionally, many copper minerals are formed through the dissolution of primary minerals, followed by their reprecipitation under favorable conditions. Metamorphism of country rocks caused by changes in temperature, pressure, or stress can also result in the formation of new minerals. For example, minerals such as kyanite, sillimanite, and staurolite are produced through metamorphic processes. Section 2. Formation of minerals. Minerals are formed through the process of crystallization, which is the growth of a solid from a material whose constituent atoms combine in proper chemical proportions and a well-defined crystalline structure. For example, in diamond, a covalently bonded mineral, carbon atoms are arranged in tetrahedral units. Each tetrahedron is linked to others, forming a regular three-dimensional structure. As the crystal grows, it extends this arrangement in all directions by adding atoms in the correct geometric pattern. In sodium chloride, NaCl, an ionically bonded mineral, sodium, Na+, and chloride, Cl- ions, are arranged in a three-dimensional cubic structure. Each ion is surrounded by 6 ions of the opposite type, forming a repeating cubic lattice. Crystallization begins with the formation of microscopic crystal nuclei, which have natural flat surfaces known as crystal faces. These faces represent the external expression of the mineral's internal atomic structure. For instance, cubic crystals of halite reflect its internal cubic arrangement, while the hexagonal shape of quartz corresponds to its internal atomic structure. As crystallization continues, crystals grow larger while maintaining their shape, provided they have enough space. Large, well-formed crystals develop when growth is slow and uninterrupted, typically in open spaces such as fractures or cavities in rocks. In contrast, glassy materials form when liquids solidify so rapidly that atoms do not have time to arrange into an ordered structure. These materials lack crystal faces and instead have irregular, curved surfaces. Volcanic glass is a common example. Section 3. Conditions for mineral formation. Minerals form under various physical and chemical conditions. 1. Cooling of liquids. Crystallization occurs when a liquid cools below its freezing point. For example, water forms ice crystals at 0 degrees Celsius. Similarly, magma crystallizes into solid minerals as it cools, often at temperatures around 1000 degrees Celsius, forming silicate minerals such as olivine and feldspar. 2. Evaporation of solutions. Minerals can form when dissolved substances precipitate from a solution as the solvent evaporates. For example, when seawater evaporates, it becomes saturated with salt, leading to the precipitation of halite, rock salt. 3. Rearrangement in solids, metamorphism. At high temperatures, typically above 250 degrees Celsius, Atoms within solid materials may become mobile and reorganize into new crystal structures. This process leads to the formation of new minerals such as mica under metamorphic conditions. From the depths of magma to evaporating oceans to intense heat and pressure, minerals record the entire history of our planet. If you want to explore more amazing geology topics, subscribe to Geology Wonders and keep discovering the Earth.